Hi everyone, my name is Ihan. I'm gonna do the question 2 of homework 10, so let's begin. So it tells that from lecture notes to collect some definitions of properties of some stochastic processes. So the first one will be a wide-sense stationary process, also called WSS. So the definition of it will be, we see that a real stochastic process xt is stationary in the wide sense, which is WSS, if its expected value is a constant and its autocorrelation depends on t1 minus t2 only, and we also call it tau. So in mathematical way to express it will be the expectation of xt equals to eta, which is a constant, and this is the autocorrelation actually. So the autocorrelation is equals to expectation of xt plus tau times xt will be equal to r tau, tau which stands for t1 minus t2 actually. And we know that actually Poisson increment process, Poisson impulse process, and random telegraph signal are all WSS. While Poisson process, semi-random telegraph signal, random walk, and Wiener process are not WSS processes. And we know if a stochastic process is a WSS, directly means it is a SSS. However, if it is SSS, and we have to add another condition that expectation of xt squared actually exists, then we can prove that it is a WSS. And we know that if input xt to a linear time invariant system is WSS, then the output of this system is also WSS. And the second stochastic process will be independent increment process. And the definition of it is xt is a process with independent increments if the probability of xta minus xtb smaller or equal to x1 and xtc minus xtd is smaller or equal to x2 equals to the multiply of these two probability for any non-overlapping intervals. So these independent increments actually implies uncorrelated increments. And we know that the Poisson process, random walk, and Wiener process are all independent increment processes. And the third one will be Markov process. And we see that the definition of it is that we see that a process xt is a Markov process if the past has no influence on the statistics of the future, under the condition that the process present is not. So a mathematical way will be the probability of xt1 is smaller or equal to x1 under the condition xt2 equals to x2 to the xtn equals to xn. It is equal to the probability of xt1 is smaller or equal to x1, and under the condition xt2 is equal to t2. And it is statistically determined by the second order probability methods. And we know that Poisson process, semi-random telegraph signal, random walk, and the Wiener process are all Markov processes. Then the fourth one will be the normal process. And we know that a process xt is said to be normal if the random variables xt1 to xtn are jointly normal for any n t1 to tn. And that is, this is the mathematical way to write it. And here where x equals to x1 to xn and the capital X, xt1 to xtn. And this eta is the expectation of x, and the c is autocovariance, the expectation of x minus eta times x minus eta's transpose. And the statistics of normal process is completely determined in terms of its mean eta t, which is the expectation, and rt1 t2 is autocorrelation, or the autocovariance c t1 t2. And the number 5 would be a strict sense stationary process. The definition of this xt is SSS if its statistics is not affected by a shift on the time axis. A mathematical way is fx x1 x2 to xn t1 to tn and equals to the fx x1 to xn t1 plus epsilon to tn plus epsilon. It is true for any n and any t1 to tn and any epsilon. And we know that actually any sequences of LID random variable is a SSS process, and we have some properties of SSS. First will be if xt is SSS, then we know that fx xt is equal to fxx, which means it's independent of t. The second will be the expectation of xt is a constant if it exists. And the third one will be fx x1 x2 t1 t2 will be equal to fx x1 x2, and here's t1 minus t2. And the last one will be the r t1 t2 equals to the r t1 minus t2 if the expectation of xt square exists. And that's why we know that if our stochastic process is SSS, we need to know that its expectation of xt square exists, and we know it's WSSS. And we know that if input xt to a time invariant system is SSS, then the output is also SSS. Okay, so the next stochastic process is the white noise. And we see that Vt is a zero mean white noise if RVT1 T2 equals to QT1, which is what we call average intensity times the epsilon T1 minus T2 is the impulse of T1 minus T2. And we know if Zt is the Poisson impulse process, then the Vt equal to Zt minus lambda is the white noise, where Q equals lambda. Here lambda is actually the expectation of this Poisson impulse process. And we know that the d dt wt is a Gaussian white noise, where wt is a Wiener process. And we also have some properties. First, if xt is WSS white noise, then the qt will be equal to q. The expectation of yt square will be equal to the q times the integral from minus infinity to infinity h lambda squared d alpha. And if ht is of short duration relative to the variation of qt, then we have expectation of yt squared equals to the integral from minus infinity to infinity qt minus lambda and h lambda squared d alpha, which approximately equal to qt times the integral from minus infinity to infinity h alpha squared d alpha. And last one, if RVT equals to the q times this impulse t, which means it's a WSS white noise, and Vt is applied to the system at t equals to 0, we have xt equals to Vt times the ut. And the seventh one will be a mean ergodic process. Mean ergodic process, and with the definition of it is that xt is said to be a mean ergodic if this limit limit to t to infinity 1 over 2t times the integral from minus t to t xt dt will be equal to the expectation of the xt in mean square sense. And here the expectation of xt equals to it, it must be a constant. And here are some ways to prove that it is mean ergodic. First, xt is mean ergodic actually is equal to the limit of t to infinity 1 over this is the 2t squared. The integral from minus t to t another integral from minus to t, c t1 t2 dt dt2 equals to 0. And here's another sufficient and required condition, which is the limit t to infinity 1 over 2t times the integral from minus 2t to 2t c tau times the 1 minus tau's absolute value over 2t dt equals to 0. And here are two just sufficient conditions which are not actually required. We know that xt WSS, and if xt is WSS and we have this integral smaller than infinite, then we know that is ergodic. And another one will be if this WSS and this limit is 0, then we know that xt is the main ergodic. Okay, so the last one will be martingale. So definition of it is a martingale is the stochastic process for which at a particular time the conditional expectation of the next value in the sequence is equal to the present value regardless of all prior values. And its expectation of xn plus 1 and the condition x1 to xn will be equal to xn. And we know that a martingale is actually a tool to control animals, so it's all relevant to control. And we know that actually random walk and Wiener processes are martingale processes. So that's all for the question 2. Thank you.